Okay, when we form an aqueous solution of an ionic compound, that ionic compound undergoes a process of dissociation. That is, the ions that make up the ionic compound will separate from one another in the solution. And so, in general, if we have a metal present in a compound, we're going to call that an ionic compound. But ionic compounds can be a metal and a nonmetal, a metal and a polyatomic anion, or a polyatomic cation and some anion. And so when we dissolve ionic compounds in water, they undergo this process that we call dissociation. That is, the ions become separate. Okay, so for example, when we dissolve potassium chloride in water, the formula is KCl. That potassium, when we dissolve it in water, forms aqueous potassium ions and aqueous chloride ions. In solution, those ions are no longer associated with one another in an ionic compound, but rather they form separate ions in solution. So for every 1 mole of potassium chloride that we dissolve in water, we get 1 mole of potassium ions and 1 mole of chloride ions. The same is true if we are dealing with polyatomic ions. So if we take cupric sulfate or copper 2 sulfate, when we dissolve this into water, we get a separation of the copper 2 ions, that is Cu2+, and the sulfate ions. So in this case, our polyatomic ion remains as a polyatomic ion in solution. Okay, and so these atoms within the sulfate ion are bonded together in covalent bonds, though there is a net charge. So for every 1 mole of cupric sulfate that we dissolve, we get 1 mole of copper ions and 1 mole of sulfate ions. Now, depending on the formula of our compound, we will get different numbers of ions in solution. So for example, instead of potassium chloride, if we had potassium sulfate, because sulfate has a 2- charge and potassium has a +1 charge, that will mean we have 2 potassiums for every 1 sulfate. So for every 1 mole of potassium sulfate that we dissolve in water, this separates into 2 moles of potassium ions and 1 mole of sulfate ions. Now, when these ions dissolve in water, forming an aqueous solution, the ions themselves are separate from one another, and they are held apart by the interactions of water molecules. And so here, this cartoon sort of shows the types of interactions that are going on in the water. So the ions aren't actually separate all by themselves, but rather they are intimately associated with water molecules in what we call a sphere of hydration. So when we take sodium chloride, for example, that is initially in a crystalline structure in which all the ions are nestled right next to each other, the anions making favorable interactions with the cations here. When we put this into water, these ions again dissociate from one another and they become surrounded by water molecules, again what we call a sphere of hydration. And so it's these water molecules that prevent the ions from coming back together and forming a new ionic bond. And so when we talk about an aqueous solution, this is the situation that we are dealing with. We are dealing with hydrated ions that have separated from one another. So when we have an ionic compound, we can imagine that whatever our initial formula was, those ions present in that initial compound are going to be separated in solution. So for example, in an aqueous solution of potassium chromate, we will have 2 moles of potassium for every 1 mole of potassium chromate that we started with, and 1 mole of chromate ions. For barium nitrate, barium has a 2+ charge, and so there are 2 moles of nitrate for every 1 mole of barium, and when we dissolve this in water, these ions again become separated from one another. Now, determining whether or not a chemical reaction will occur when we mix these two solutions in this example depends on the solubility of the possible products. So just to clarify a little bit vocabulary, when one substance dissolves in another, we say that substance is soluble, and we call that substance that is dissolved, we call that the solute, and the solution, or the liquid that it dissolves in, we call the solvent. In most cases, this is going to be water. So we know that sodium chloride, or table salt, is soluble in water. When we add crystals of sodium chloride, they will dissolve and appear to disappear. But when we're dissolving, again, remember, we have now separate ions in solution, separate hydrated ions. If a substance does not dissolve in water, we say it is insoluble. We know that oil and water don't mix, for example, and that's to say that oil is not soluble in water. It's insoluble. Okay, and we won't consider gases at this time. So, in many cases that we will observe in both the laboratory and in lecture, when we mix two aqueous solutions of ionic compounds, we have the possibility of forming an insoluble ionic compound. That is a compound that is no longer soluble, and we call this a precipitate, or a precipitate. Okay? And we can see the evidence of a precipitate quite clearly because our solution will get cloudy, and over time this solid that is suspended within the water will slowly settle down to the bottom. Now, in order to be able to predict the identity of this ionic substance that is formed, the insoluble precipitate, we are going to follow a couple of standard rules. Okay? The first thing we want to do is to write the reactants as they existed before any reaction occurred. That is, we are going to separate the ions and write what we sometimes call a full ionic equation. We're then going to consider the possible products that could form by exchanging the ions. That is, to take the anions and hook them up with the other cation and predict the possible products. And then we are going to use a simplified set of solubility rules to decide which of those products is soluble and which is not. So let's take our example of potassium. Let's first talk about these solubility rules. So there are a number of factors that affect solubility that we won't go into right now, but really, if we remember two very simple rules, we can predict whether or not a precipitate will occur in 80 to 90% of all cases. Okay, and what we want to focus on here are really just these first two rules in this table. Now, your textbook has a similar figure to this, or similar description of these solubility rules. But basically, if we remember these two simple parts of this table, and that is that any salt that contains the nitrate ion, whether it's sodium nitrate or silver nitrate or ferric nitrate, any nitrate salt, any salt containing the nitrate anion is soluble. So anytime we have a precipitate, that precipitate will not contain nitrate salts. It will not be a nitrate salt. The other simple rule is that all salts that contain sodium, potassium, and ammonium will also always be soluble. So sodium chloride is soluble, sodium sulfate, any sodium, potassium, or ammonium salt will always be soluble. And so we can use these two simple rules to rule out any of the possibilities and allow us to predict what our products are. So, well, let's jump in the gun there. Okay, so let's come back to our example of potassium chromate mixed with barium nitrate. So in order to predict what the identity of that precipitate is, we are going to first start off with our reactants. So we have potassium chromate plus barium nitrate, and that goes to form some precipitate, and we want to be able to predict what that precipitate is. to do this, we're going to first identify the ions that are present in solution. And so we will write, we have K plus, we have CrO4 has a 2 minus charge. We can tell it's a 2 minus because we have 2 potassium ions here. And again, this is a polyatomic ion. And then we have barium ions. And we have nitrate ions. Okay, and what we want to do now is to get our tool out, sorry, is we want to imagine what compounds could form by swapping the anions. So we're going to take the chromate and form a compound with barium, and then we're going to take the nitrate and form a compound with potassium. And so our possible products that we could form are barium chromate. We have a +2 and a -2, so these will come together in a 1-to-1. So one possibility here is barium chromate, and our other possibility is potassium nitrate, KNO3. Again, we have a -1 and a +1 here, and so they will come together in a 1-to-1 ratio. And now we're going to look at these two possible products and ask which of them is definitely soluble. And so again, following our rules, okay, if we have a nitrate salt, that is definitely soluble. And if we have sodium, potassium, and ammonium, that is definitely soluble. So when we look at these two possibilities, we see that potassium nitrate has both nitrate and potassium ions, and so this is definitely soluble. That leaves us as barium chromate being our precipitate in this case. And so this is what we call a precipitation or a double displacement reaction. And so this allows us, by separating out the ions, to predict what product, if any, that we have remaining in our solution. Okay, and so after the precipitation event has occurred, we initially start out with these separated ions, the barium, potassium, nitrate, and chromate ions. And when the barium and the chromate ions come together, they form this insoluble solid that we again call a precipitate, and the potassium and nitrate ions are still left in solution.